So, good evening to all participants. We will be starting day 3 of the FDP. It's 6, and few of the participants are like still uh, they have joined, and some are like still pending. But we'll start the session as our speaker for today, Colonel Amit Oberoi, has already joined us. I will give a brief introduction about him. So, welcome to you, Dr. Amit Oberoi. Can I present my screen for some time?
Hello, good evening, ma'am. Yeah,
Colonel
please,
Oberoi,
sure.
yeah, good evening.
Please do it.
Yeah, so I'll just present. Yeah, okay. Parul, is the screen visible?
Yes, ma'am.
Okay, so
It's coming.
okay, so today's topic for this session is generative AI
Voice is not clear.
applications. Focusing on natural. All right, just give me a second, please. Is everyone having a problem with the sound quality?
Yes,
Parul?
Ma'am, it
your voice was
was, but
getting cut
now it's coming.
intermittently.
It was, but
Now it's
now it's
okay.
coming properly.
Now it's okay? All
Yes, ma'am,
right.
now it's okay.
Okay. So I'll start again. Colonel Amit Oberoi has over 25 years of technical experience in the Indian Army, focusing on natural language processing, deep learning, and cybersecurity. He has served in roles like Senior Director, Commanding Officer, and Head of IT and Cybersecurity, with expertise in knowledge representation, context extraction, and multimodal analytics. As part of ITU Study Group 12, he introduced the concept of quality of emotional experience for future NLP applications. Colonel Oberoi has significant experience in planning complex communication networks, having commanded a Strike Corps signal regiment and led satellite communication projects for the Indian Army, including the IA satellite GSAT 7B and over 5 emergency procurement projects. He has been a faculty member at the Indian Army Training Team Lesotho, Military College of Telecommunication Engineering, and College of Defense Management. A gold medalist in engineering and the highest CGPA awardee during his MTech at IIT Delhi, he has also worked on software defined radio projects at IIT Delhi. He has worked on complex AI problems based on both discriminatory AI and generative AI and has productionized an on premise, multilingual, secure LLM based knowledge agent for corporates and government agencies. We welcome you, Colonel Oberoi, and we hope that this is going to be a very interesting session for our participants. So, over to you.
Hello, everyone. Very good evening to you, Dr. Preeti Singh, and all the
Good
participants.
evening to you.
And I just wanted to ask you that I think I have about an hour to cover this particular topic. And I just wanted to be clear about the rules of the game before we go ahead further. Is it an interactive session wherein I can ask some of the participants to contribute so that I just know whether, somebody, their knowledge or their level of expertise? And the other part is that if somebody really
Yes,
wants
I
to ask a
think
question,
yes,
it is
yes,
interactive,
yes, of
right?
course. This is going to be an interactive session. Yes, the participants are free to unmute themselves and like engage with you. So in case they have
What
any
we will,
doubt or any
right, right.
topic.
So if somebody wants to, has got a pressing requirement of asking anything, he can actually raise his hand, right? And we'll request him or her to unmute their
Yes.
mic. But there are, I think there's a large number of participants here. So if too many speak, then we can get interrupted. So that is one. The other aspect is
Yeah, I
that,
think raising a hand would be a good idea. Yes.
yeah. And have they covered AI before this, before generative AI?
Uh, Kanal Oberoi, so there was a session on trusting about different flavors of AI and what are the challenges. But AI is such a
Okay.
broad topic. So what exactly are like wanting as a prerequisite?
No, I mean, I just wanted to know whether how many of them generally are aware of AI before I touch upon generative AI, because I will then maybe, cover a few aspects of AI. But anyway, I do understand maybe some of them must not have consciously touched AI during the FDP. So rather than using up more time, what we'll do is we'll start immediately. I will also join up from
Yes.
another machine, right? I think I am already online from my other machine, wherein I think I can present, because I will be drawing a few things. Just a minute. Mm, yeah, and I will be off and on switching my focus from the presentation to something which is handwritten. I'm just wondering how to share the screen here. Just a minute. In call adults activities. Uh, I should be able to share my screen here. Have you not allowed sharing screen for anybody else? Can you give me a screen
Well,
sharing on my other account as well? So you will find me
uh,
as OB. I'll just tell you who I am on the other account. Just give me a second so that I can. Just a minute.
well, I think only one speaker or
Yeah.
one
No,
participant
I can
can.
I can share my screen. Just a minute.
Yes, yes, you can.
Yeah.
But at one point in time, either of the accounts would be able to
Yeah.
share.
Yeah. That's fine. Just a minute. Okay. Right. I think we are good now. Right? Okay.
Yes, yes, yes.
We are good now. And basically, I would like to, cover a few things while writing as well. So, very good evening to everyone. And today, I will attempt to cover So today I will try and cover this particular agenda with you. That is, I'll touch upon AI and generative AI and characteristics of generative AI. I'll touch upon predictive machine learning versus generative AI. Then what are foundational models, right? Then I will cover one of the So we already know that AI can do all this. AI can play chess, it can play Go, make purchase decisions, drive a car, write an essay, etc. And when we look at types of AI, and when I brought out it is discriminative and generative AI, one other method of classifying AI can also be strong AI and narrow AI. And when you look at the strong AI, then you are looking at comparing AI with the intelligence of a human being and a machine that can solve problems, learn, and plan for the future, and which is an expert at everything. Whereas you may call it narrow or weak AI, though it is not very weak, but then it is very application specific. So one view of classifying AI could be like this. Now we come to generative AI. So what actually generative AI is able to do for us is it can generate new content, right? Some new content such as text, images, audio, etc., based on certain amount of latent information which is available with us. And what that latent information is, I'll cover shortly. Okay. Now, certain examples which we have already been using is ChatGPT, DALL-E, Midjourney, okay, GitHub Copilot. In case you use GitHub, you'll find nowadays all these particular softwares have got copilots. And there are a number of applications for generative AI. Some of them could be content creation, some could be healthcare, some could be finance, market prediction, synthetic financial data generation, etc., and all that. One of the most important aspects. So the difference between traditional AI or discriminative AI and generative AI is while traditional AI can do predictive analytics, it can carry out fraud detection, it can do a classification problem, it can do a categorization problem, it can do a business process automation, it can take out some recommendations based on the learned data which is available with it and the way it has been trained, and whether it's a machine learning problem or a deep learning problem, etc. Generative AI can generate data for you. And one of the very important applications of generative AI is synthetic data generation. So what is meant by synthetic data generation is that you are able to generate synthetic data for applications where the data availability is very, very minimal, right? For example, let's say there are certain scenarios in cybersecurity wherein you have threat intelligence, but you don't have threat intelligence for certain scenarios wherein, let's say, the entire power sector of a country can be brought down. So you can generate synthetic data based on certain characteristics. Let's say you need to train a model which can fire missiles using models trained on thermal imagery. Okay. But you do not have the thermal imagery data of the enemy tanks available to you. you have the normal images of the enemy tanks available to you. From the normal images, the RGB images which are taken during daytime, you can use generative AI to guess what would be the thermal images. And if the generative AI is good, those thermal images can be used to train a model to work on, so that synthetic data can be used to train a real world AI model, right? Which can be used in missiles, and be effective in the night, right? On thermal images which have not been seen. In a similar manner, for medical diagnosis, if you have, let's say, imagery over 5 years, okay, of a person, whereas tumor is, let's say, a very small tumor right now. After 2 years, it was becoming big, it was benign. Then another 2 years, it was becoming big. Today, it is again bigger, but it is still possibly benign. But you're not sure whether it is benign or, non-benign, malignant. So what you can do is you can use generative AI that 5 years back, whatever was the tumor, in similar manner, if it was malignant, what was the tumor looking like? And after 5 years, it is now becoming so big. Now you compare that whether it was a normal tumor or whether it is a cancerous tumor, and you look at generative AI, look at the time slices, and you can use generative AI to find out causality between the present day image and go back and check whether, if it was cancerous, it would have looked like this. If it was benign, it would have looked like this. I hope I can actually, make you visualize intuitively what I mean to. So generative AI has got tremendous number of applications apart from the applications with ChatGPT, which you see in front of you. So how is generative AI different? Certain aspects, it needs a huge amount of data for training. So OpenAI, as we are already aware, ChatGPT, etc., have been trained on a huge amount of curated data. If you go into detail, in fact, there are lawsuits, there are telltale signs in which people have been, complaining that they have not been paid adequately for annotating that data. It uses a part of self-supervised learning and uses tokens instead of words. So when I say tokens means, when you look at natural language processing and you look at a particular sentence, then it looks at the full sentence. In fact, it looks at number of sentences together, and the start of the sentence is a CLS token. Then you have the entire word, then even the stop word is a token. So everything is a token, right? And the size of the tokens, the number of tokens which can be used. So please, I'm going a little bit fast in the sense, each one of them, right? Like natural language processing, tokenization, word embeddings, each one of them is a session in itself. So I have to combine all that. But please imagine intuitively what I'm mentioning is each one of them is a token which gets embedded to create an embedding, right? And with generative AI, all these tokens together mean something. Okay. I'll touch upon something called as the transformer architecture, how it has come up and what is special about it. But please understand that we are now looking at context. So how is generative AI different is, we are looking at context in addition to the immediate meaning of that word or that photograph or that segment of that photograph or the segment of that image. Okay. So in some sense, the present day models, after the advent of the transformer architecture, have started understanding the context. Okay. And like I drew the diagram before, you have AI, machine learning, deep learning, and generative AI. Okay. Now, when you look at the history and evolution of generative AI, okay, so AI, the evolution of AI is from 50s onwards. But when you look at generative AI, when we started generating, we started looking at natural language processing initially. And on top is something which was for language models. Okay. Today we have GPT-3, BART, T5, etc., Sparrow, Chat GPT, etc. And down below are the visual models. And we have the visual language models also today, which are in place. Okay. So we have the early foundations were based on rule-based systems, Markov chains. People emulated and made, algorithms which used to emulate Markov processes. And in a Markov process, it's a memoryless process in which the previous state does not depend upon the state previous to that. So one state depends upon a state only one previous to it and not more than it. Okay. Then came the neural networks, and today we have sequence-to-sequence models and the transformers, which is a revolution in understanding context. So context is something which I will request you all to remember. So the basics of generative AI is that you have something called as a foundational model, right? Which has got many number of downstream tasks, which the same foundational model can be used for number of downstream applications with little variation. And that foundational model has been trained on a large, huge amount of data set. Okay? Because it has been trained on a huge amount of data set, it now can be used for answering questions and analyzing sentiments, information extraction, image captioning, object recognition, and instructor following, etc., and all that. Okay. And when we look at text, then we have the GPT model, sentiment analysis, etc. When we look at images, then we talk of GANs and variational auto encoders. I think we'll have to mute somebody who's unmuted his mic.
सर
you are
आपने
not
अपने
audible.
आप को भी म्यूट कर लिया.
You have been muted.
Yeah, no worries.
Yeah.
Right.
Participants, please
Now,
keep your mics off. Otherwise, it
okay.
causes unnecessary noise.
Okay. So not to worry. Till now, anybody has got any doubts, any pressing doubts? Yeah. Anybody, any doubts? Please feel to interact with me. Okay. Let me ask anything else. Has anyone here, right, used generative AI in some form for an application? Okay. Not that you have used ChatGPT or you have used this thing. Have you used it in some form in making an application? Anybody would like to contribute?
Sir, I had given only an idea for some gesture recognition. You can
Okay.
assume like a sequence of gesture recognition, basically for sign language. So
Okay.
in that case, I found the problem that if my left hand to be somewhere at some location, then if I
Right.
go for the generation, can there be any idea like generating the sequence? Similarly, can I hope you can understand my question.
Yeah. Yeah. So, what you are saying is that can we word, third word, fourth word. Using these words, you send it to a single neural network layer, considering. So what is this? This input is 1 cross 10,000. 1 cross 10,000. 1 cross 10,000. 1 cross 10,000. And this word is I like to fly. Let's say not even to. So let's say I fly in the sky. Right? So let me just change this. Yeah, or I say bird flies in the sky. Bird. So flies become fly. In is not a word. It becomes in the sky. And this is not a word. Okay. Just giving you a small example, right? And you give it to a feedforward neural network, which is 1 cross 300, one single layer. And from it, you derive a single output here. Okay. Now what you do is, instead of giving the input here, you say bird, fly, sky. You need to take out fly from here, and you say this fly comes here. I remove fly from here. So I remove fly here, and I say bird, sky. Because fly is there, it should be able to predict fly. So what are the weights of this neural network? Those weights are 1 cross 300. So what am I doing? I am doing something called as a bag of words technique. Okay. It is something called as a CBOW or a skip gram technique. Because of paucity of time, I cannot go into too many details, but please try to understand a very simple concept. So this is a fully connected layer. So this is a matrix of, let's say, 3 cross 10,000, out of which one I have made blank. I am trying to guess fly. So I fix fly here, bird is here, and sky is here. So what am I trying to do? I'm trying to say, okay, this 1 cross 10,000 now can be represented by this 1 cross 300. In other words, I am trying to compress that information of 1 cross 10,000 into 1 cross 300. This information, in some terms, can be called as a basic latent information, which contains a vector, which is not a one-hot encoded vector, which each of those values will be different, but it represents bird. Okay, that word bird. Similarly, another vector will represent fly, which is 1 cross 300 vector. And all these words will have some meaning which are correlated with each other. So when you plot these vectors and you find that if this is bird, this is sky, right? They will come close to each other because bird flies in the sky. This is fly, right? Now, if there is elephant can be coming close to bird, but it will not come maybe close to sky. Similarly, the very typical example in natural language processing that we give is king is as close to queen as a man is close to woman. And king is closer to man, queen is closer to woman. Okay. Are you with me? Right? This basic concept. Now, why am I covering this basic concept? It's very important to understand a basic introduce the transformer architecture. After we thought of the transformer architecture, it came through a paper called as Attention is All You Need. This came up in 2017. Please read about this. This paper is not easy to understand because it contains the transformer architecture. It took me around a year, 1 year, repeated readings to understand the transformer architecture in detail. Okay. But what I am telling you right now, right, is my understanding of the entire architecture is that with this transformer architecture, you can understand context. How can you understand context? A simple sentence saying that I am going to the bank, right? Now, this is a simple sentence. Now, have I been using the previous thing? Each of these words is now a token. It represents something. But the token has a very different meaning when I say I am going to the bank to withdraw money. And it has a very different meaning when I say I am going to the bank to swim or to fish. The meaning of the bank completely changes when this bank comes with money, when this bank comes with swimming, when this bank comes with fishing. In the first case, it is the money bank. In the second case, it is the river bank. Right? Why does this happen? It happens because in the transformer architecture, right? Architecture, each of the word is correlated with every other word. So the entire sentence or the group of sentences correlated with the other sentences, and each has got something called as a positional embedding or a positional encoding. So the position of each word and the sentence makes a difference, right? And now when I create an embedding out of it, after passing it through multiple layers of deep neural network, I compress that and I create an embedding out of it. It results in a particular vector wherein this whole sentence, the meaning of this sentence is very different from the meaning of another sentence, I am going to the bank to swim, right? In short, the context is being understood by this architecture, and the embeddings are very, very enriched because now for every token, the embedding is separate, and we can do a mean pool, max pool, etc., and all that depending upon what is the model that you select. Most common transformer, the early transformer architectures, and most common and efficient architectures for embedding is the BERT architecture, which people use. Okay, I cannot go into more detail than this because I think I will really fall short of time. I actually need maybe 2 hours or so, but let's go further ahead. Okay, let's go further ahead. So this is one method of making an embedding, which can be used for multiple things like classification, sentiment classification, because now that embedding which you have created has an enriched embedding. Now you put a deep neural network ahead of that and you train it for sentiment classification. You can train it for many other things, for emotion recognition, etc. And you will see the performance is very, very good because each sentence, the meaning is understood very, very deeply. Right? Another aspect, there is something called as an autoencoder. In an autoencoder, what you do is you take a fully connected deep neural network layer. Just imagine there's a huge network. The input, you make it equal to the output. Now, this is very, very naive, the way I'm telling you, but this is for a very, very basic understanding. Okay. For those who have already read autoencoders, please pardon me. It's not so simple, but please try to understand when I make an input equal to output, because the fully connected layers are connected with each other and they do a back propagation, they adjust their weights. So imagine this is a deep neural network, right? So the entire weights get adjusted in a manner. So if I'm putting a photograph, if I'm putting my photo here, I have again my photo here. The entire photo, my one photograph, let's say 1 megapixel photograph, right, consists of how many data points? It consists of RGB into 1 megapixel. So RGB, each RGB is encoded into 32 bits, etc. So it's a huge amount of data, whereas the deep neural network can be, let's say, just a small network of, let's say, a matrix which is 300 by 300. Okay, and this RGB image I say is equal to this RGB image. So what is happening is I'm actually using an autoencoder to compress the entire image. So it can be image, it can be text, it can be video, it can be any amount of information to something called as the latent space. And this is what is latent space. When you extend that autoencoder into something called as a variational autoencoder, in which you use a particular distribution, you slightly vary that distribution. So from this latent space means this particular weights, next time, this weights represents my photograph. Clear? The moment I do a little bit of variation to this particular latent space, I can keep changing certain features in my photograph. So when you come to variational autoencoder, you do a probabilistic estimate, you add a little bit of variation to that, and I can generate different photographs which may look like me, but they don't look like me. So I can generate something. So an autoencoder is not generative AI, but variational autoencoder, the moment you start varying certain features there, it starts becoming generative. Okay. The last part is something called as diffusion models. Why am I covering this is because if I cover in the presentation, I can just go fast. You will not understand anything. But these are main concepts which I just want you to understand. All right. Now in diffusion models, the diffusion models are models which basically are trained in a manner that they can generate an image from random noise. So how does it happen? Okay. You can say, I will not say only image, you can say information, but let's talk of an image. Okay. So you have an image. So there is an image. Imagine it is again my photograph. You add little bit of noise to it. You add noise to it. You have a noisy image. So the noise comes as my image with some noise. You understand this process. There are some methods to understand this process. Similarly, you keep adding noise at each step. Till the time the entire image, what will happen? My image will no longer remain. I will become dust. I will become completely noisy. Right? With me? If I can understand this process of the addition of noise, and if I can understand this particular distribution, then I can recreate my image from only noise. And completely, let's say Gaussian noise, I can generate my image if I know the process. Okay. In a manner that you put a drop of ink into a glass and the way it diffuses, if you can reverse that process, imagine you're rerunning that video, that diffused water, that blue water can go back and create that drop by itself. So that is what is diffusion all about, right? There are a lot of advantages of diffusion as long as you have. So when you look at generating images of cat, or you can say generate an image of a cat which looks like a dog, or a cat which has got a tail like a monkey. So all those things are because those distributions are available, they are captioned, and then they get mixed and matched and more so. But I don't want to confuse you. Basics of diffusion is this. And the last part is GAN. GAN is a generative adversarial sorry for the spelling, network. Okay. Basically, GAN is nothing but a combination of a generator and a discriminator, which are nothing but two neural networks competing with each other to make an image a synthetic image. So the discriminator has been trained on actual ground truth data, right? Let's say that you have to generate the image of a woman. Okay. The generator generates the image of a woman. The discriminator says whether this image is a real woman's image or a synthetic image of a woman, which is not a real image. Okay. Till the time the generator keeps generating the image. So the discriminator, and you know whether the image is a real image or a non-real image. Okay. Till the time the generator keeps generating an image. Okay. And the discriminator, the moment the discriminator says this is not a real woman, and it is actually not a real woman, the discriminator wins. Then the generator generates a better image. It starts learning. Okay. So both generator and discriminator have to be fine-tuned. There are some pitfalls of using a GAN architecture, but the GAN architectures can create very, very genuine looking images and very, very genuine looking videos. And we are all aware of the deep fakes, etc., which are generated using similar architectures. Okay. And if they both are very well balanced, then based on the training data set that the discriminator has been trained on, the GAN architecture is capable of generating very high quality synthetic images. Okay. And they can be slightly variation with each other, etc., and all that. So there are certain pitfalls for both of them. So there are a few things which I have just covered before you. One is takeaways for you. And after that, I will go to the presentation and move fast. Takeaway number one is it's all about the embedding. Okay, how well can you create an embedding to represent the knowledge? And that is why knowledge representation and embedding is most important. Second is the transformer architecture was instrumental in having generative AI. Third aspect, which I actually should have mentioned to you, is this BERT models and the LLMs are basically models which have been trained with these enriched embeddings encoded and trained to predict the next sentence based on the previous sentence. So they actually are trained on something called as the next sentence prediction and masked language modeling. This is very interesting. So the thing is, they have been trained that if there is a sentence like this, the next sentence can be this. And when the next sentence comes, it becomes recursive. What should be the next sentence, etc., and all that. Okay. And they've been trained in a manner because those embeddings understand that this sentence is very unique, because this sentence is used in context with its previous sentence, which is used in context with its previous sentence, right? And therefore, the LLMs, which basically are next sequence prediction or the next sentence prediction models, are able to perform so well. Attached with the LLMs are the visual language models. The visual language models, in a similar manner, can firstly classify images, can understand the context behind the images. So if I am standing, okay, and I'm running desperately, it will say, okay, a man who seems to be desperately running. And if there is something behind me, something damaged, so possibly something has got damaged or there's somebody met with an accident. So it can see the entire image. It can understand the context behind the entire image where that thing is placed. Okay, because of the positional embeddings, where what is. Okay. I cannot go into more details beyond this. I would have loved to, provided we have a full course of generative AI, etc. But now allow me to go through the presentation. I will share this presentation with everyone. There's nothing very great in the presentation, but what I wanted to share with you were these basic concepts. It's all about the embedding. The transformer architecture is successful in looking at the context. Large language models are models which are able to carry out good amount of encoder. They have an encoder and a decoder, and they use next sequence prediction to generate the sentences ahead. Then you have autoencoders, which convert that entire information into latent space. And when you vary that with some sort of a probabilistic distribution, you have the variational autoencoders. Then you have the diffusion models. Then you have the GAN networks, okay, to generate images and real life videos, the advanced versions of these. Now I will stop sharing my other screen, and I will share the presentation with you now, and we will go fast because I think I have covered the main core concepts. I will go over the presentation and I will tell you what all things you should look at the presentation in your own time. I want to stick to the time available to me. So the generative AI is basically a reward model. Just a minute. I want to go back to what am I sharing so that I have a feedback. So the Gen AI is basically a reward model in which you have a prompt, then you process it, then you generate the output, and the output is, remember, next sentence prediction as far as the LLMs are concerned. For the GAN networks, it is competing with each other. So there's a difference between predictive ML and generative AI, right? I had covered this. Then you have foundational models. So what are foundational models? In which basically you have a number of downstream tasks which you can take off from those foundational models. They can be used for multiple tasks. So for example, let's say the Llama 3.2 is a foundational model which has come up. It improves, but it's a foundational model. It's been trained on a huge amount of data where that same model can be used for multiple tasks. Okay, so foundational models are trained once. Same model can be used for multiple tasks. For example, chatbots, classification, summarization, etc. Then you have the large language models. So some of the large language models are listed here. There are many more large language models which are coming by the day. So it's a war of the LLMs. But please remember, corporates today in the present day field are not using LLMs extensively because of the problems of hallucination. The other problem is explainability. The other problem is trustability. Then there's the fact that people like OpenAI, etc., are not ready to give you assurance that they're not using your own information for their training, and they might even use your information as. So how they are using your information, because there's always an internet outbound, we don't know. The other aspect is the LLMs are becoming bigger by the bigger, because when I talk of this latent space and when you look at the entire world knowledge information, then you have LLMs which are a few billion parameters to 40 billion parameters to 70 billion to 140 billion parameters. Right, with the context window size. So the window size is the number of tokens it can process together. So if I want to use an LLM today, and let's say if I want to make an application, then I have to say, okay, what is the context window size a particular LLM supports? And that context window, the bigger the context window size, it can understand greater amount of context and process it together. But then the processing is more, it is more costly, etc., and all that. So when you start getting into the LLM world, then you realize that there is a lot of things you have to mix and match. And many a times you don't need to kill a mosquito with a sword, because you actually do not need that kind of an LLM to solve a very simple problem. Another aspect is you can use LLMs to convert unstructured data to structured data very easily. You can use an LLM to summarize a lot of information. You can use an LLM for workflow automation, etc., and take decisions and recommend some workflows to you. So encoder, decoder models, etc., they are listed here. Then you have the diffusion models. Like I told you, you keep adding noise, okay, Gaussian noise to the original data in the forward diffusion process, then learn to remove the noise in the reverse diffusion process. So this is what the entire diffusion model is based upon, okay. There's a whole lot of maths behind it. Then you look at the loss functions, etc., but that is for a different class altogether. Then you have the visual language models. So the VLMs, like the LLMs, can understand an image. They can understand the context behind the image. And you have certain models which can even understand videos. Okay. You can actually have a model, if you have the kind of processing available to you, which can give a running commentary for a match which is running. Okay. Then is the BERT transformer. The basics of the transformer model is, okay, one of the initial very good models is BERT, which can carry out enriched embeddings. I have been using BERT very extensively. BERT has got many types of BERT. One is a BERT based, BERT, case, uncased, BERT large, etc., and all that. So how does a LLM work? So LLM uses prompt engineering. Okay, there's an aspect of prompt engineering which you should be aware of. If you want to use output. So, if you want a good output from an LLM, if you follow the RTF framework, or there is a CTF framework also, context, task, and format. Okay. If you follow this, you will find the chat GPT will give you much better responses. And generally, you need to secure your LLMs by prompting it initially, and then ensuring nobody else is able to change the prompt for a particular use case application if you're using it. Let's say you're using it for customer service for an ice cream department, then you need to tell it that this is what you will reply to. You will not reply to any out of context questions, etc., and all that. And then you can implement a prompt framework like the RACF, in which you have the role, action, steps, context, examples, right? And the format. It is very interesting. It is not very difficult. It is very good to experiment with it. So basic prompt engineering example I have given you here. You can take an OpenAI API key. It will cost you very little. And you can make a small application. You can integrate it with your front end, and it will give you all the responses. I would have shown you a demo, but I think I'm short of time. You have another presentation at 7:30, and I'll try to finish it in another 3-4 minutes time. Then is a framework which can communicate with the LLM. One of the very popular frameworks is LangChain. Okay, so LangChain framework looks after everything, handling QA chain, looking at or the input output to the LLM, managing the memory, etc., and all that. It has predefined functions, so they've made things very easy for you, and it's all open source. It's all open source, and you can use the LangChain framework in your particular application, integrated with an LLM. Some of these LLMs are on-premisable LLMs, which you can on-premise on your machines. You can on-premise on a containerized environment within the cloud, like the Llama 3.2, etc., and all that. They're on-premisable. Okay. Then you have something called as the RAG framework. The RAG framework is nothing but using a database, using one LLM to understand what is the natural language question asked by a user, convert that into a SQL. I'm giving you one of the example, a SQL query or a vector database search, etc., and all that. Generating response from that SQL database, using that response and the query and the context, and responding in a natural language. For example, let's say you have a database down below that in your college, how many are boys, how many are girls, how many are good sportsmen, how many have got a CGPA above 7. Okay, so I say how many have got a CGPA above 7 in the this particular college at Jaipur, right? So the response will be okay. It will look up the database. Okay, college Jaipur, so many boys, so many girls, third year students or second year students, so many. So it will give a response that total students which have got a CGPA above 7 are 600 in this college at Jaipur. You want further queries. So how is it coming? It's coming through something called as a RAG framework. Okay, so there are a number of other frameworks, and you have to understand to implement a RAG framework. It is very easy, but to fine tune it to give correct responses and accurate responses, it requires some secret sauces in place. And generally, what we do is when you are having the response of an LLM, you need to evaluate that response, that whether it is accurate, whether it is relevant. So there are some benchmarking strategies which you need to follow. So a RAG implementation will be like this. You have a query, then you have an embedding, then you have a vector database, you have a context query, and then you generate the response and you get the response back, right? There are a number of cloud where you need to deploy your applications. So you have the AWS, in which you have key services like SageMaker, Bedrock, Whisperer. Please read about this in your own time. I just want to introduce you, and I wanted to add it in the presentation so that you are aware that these are things. Then you have the Azure AI services, certain advantages. Then you have the GCP. We use all three. We use all three for a particular application which you have deployed on the cloud. And Vertex AI, Palm API, etc., and all. Please just do a general reading. You will understand what is the difference. So there are many different types of LLMs. You have the open source LLMs. they're actually not open source LLMs. They should be called as open weight LLMs. The weights are available to everyone. The architecture of the LLM is not revealed by these people to people, right? Even the Llama does not reveal its architecture, which is open weight LLM. ChatGPT never reveals its architecture and does not reveal even the weights. So it is called, rather than open source, if somebody says an LLM is an open source LLM, please say it's an open weight LLM. So they are listed out in this presentation. You can have a look at them. You can have a look at certain domain-specific LLMs. We are working on a telecom-specific LLM right now. People are working on legal-specific LLMs. People are working on cybersecurity-specific LLMs. You need to fine-tune an LLM. You can fine-tune an LLM based upon the data which is available. You need to pre-process the data, and then you need to fine-tune it. It requires considerable compute resources. Then you have multilingual LLMs. Most of the LLMs today can understand multiple languages. You can integrate LLM response with other features like Bhashini, etc., and have a response for all the Indian languages as well. ChatGPT, etc., can understand 7 or 8 Indian languages. I was surprised that day. One of my friends was trying to teach his daughter Sanskrit, and he was using ChatGPT. It could understand Sanskrit as well. I have not checked it myself. I just hearsay. But what I'm telling you is that it's moving fast. This technology is moving very fast. And with the recent visit of the NVIDIA chairman and also OpenAI, etc., in India, they're all looking for data from India for vernacular languages so that they can touch the population. So it's a democratization of AI in some respect. And these LLMs will be capable of talking in the local language with people and understanding what a particular human needs. And therefore, the HMI interfaces will be good. But the ethical things, etc., we need to guard against. And we also need to look at whether our country's information is, or the data which is being churned by others is being used correctly or not correctly. So all these are strategic things which need to be looked at. And I'm sure some people are looking at it, but these are things which come to your mind. So then you have few shot LLMs. In few shot LLMs, you can give a simple prompt, you can give a simple example and tell it that, okay, if this kind of sentence comes, then it is positive sentiment. If this kind of sentence comes, it's a negative sentence. Then you have task-specific LLMs. Okay, open and source, closed source LLMs, I have already mentioned to you that open weight, and the other one is that they don't tell you the weights. Then you have to use it on the internet. Okay, now this is about LLM. You can evaluate an LLM using another LLM. Then there are many methods to evaluate the LLM functionality. Some of the scores are the blue scores, etc., and all that. Then is about autoencoder. I've already covered the autoencoder with you. Basically, it compresses that information into a latent space for you. You have a variational autoencoder in which you do a probabilistic function. You titrate that, and you can create different images based on the same images. Diffusion models, before slide, we covered it. Forward diffusion process. Actually, the diffusion is the reverse diffusion process. From noise, you can create an image. Okay. So the key components is basically it emulates this process, the Markovian process. The previous step depends upon the step previous to it. Okay. Applications are image generation, speech synthesis, data augmentation, and anomaly detection. Data augmentation is one of the examples. One of you only said the way you want to do it for the sign languages. Then you come to GANs, or generative adversarial networks, which I touched upon right now. So the concept is you have two neural networks. You have the generator, and then you have the discriminator. Okay, the architecture consists of the generator and the discriminator working against each other, right? And they can be used for image generation, image to image translation, super resolution, text to image generation, etc., and all that. So real world are deepfakes, art and design, healthcare, enhancing medical image quality, game development, fashion, etc. The advantages are, firstly, unsupervised learning, no need for label data, high quality data generation, diverse applications, and continual learning. Disadvantages are very important. Please understand, every technology has its own pitfalls. One of the big major disadvantages is mode collapse, in which the GAN will fail. It will not generate good quality images. Long training time, training instability, difficult to train both the networks simultaneously. So you need to, when you are making a GAN, you need to be very specific how you want to make that. And nowadays with AI, it is more of engineering and art rather than science. You should understand the science behind AI. But after a particular stage, what happens is you need to keep experimenting, titrating, then understand and visualize, think. And then, so in my concept and my complete this thing is, when I have been making applications, it is more of art and engineering rather than basics of science. Basics of science remains there. After that, you have to titrate and you have to experiment. And at many times, you don't understand why a particular model is performing the way it is. So with that, I think I have overshot by another 5 minutes. I want to leave time for interaction and questions, right? Thank you for a patient hearing. I will request you to please ask questions, if any, or anything which you have in mind. Please feel free to ask.
Participants, please, if you want to engage with the expert, please unmute yourself. If there are any questions.
I just hope I was able to give you a broad overview of what is generative AI and the basic theoretical foundation behind the whole concept. Anybody, any doubts, anything in your mind, or you want to create an application of your own, please feel free to reach out right now, or you can send this thing. Okay, Bhargavi has asked which LLMs can work on graph data. So, yeah. What we have used, I have used particularly, is using LangChain. We used LLM graph functionality. What kind of graph are you talking of? Is it a knowledge graph? Because we created knowledge graphs from unstructured data. When you look at a graph data, okay. Yes, sir. Okay. Yes. So knowledge graph. Yeah. So knowledge graphs can be understood by LLMs. I have not experimented with LLMs which can work directly on the graph data, but I am very confident I can make an application which can understand the graph data, because we made it the other way around. What we did is we had unstructured data. We converted that unstructured data into a knowledge graph. And that knowledge graph was being used by us to convert it back into some meaningful information. So what is a graph? A graph consists of a number of nodes talking to each other through links, which give the relationship between those links. Okay. So I think it's very much possible. I'll have to explore which are the LLMs readily available, but we used Lang graph for converting LLM graph functionality for converting our unstructured data to knowledge graphs. In fact, we are in the process of making some enriched graphs, which are multimodal graphs. Okay. Link, somebody was asking me, link for video generation. How is generative AI is different from recursive neural network? So it is very different from recursive neural network. Recursive neural network in the very beginning was, it just uses for RNNs. Okay, it is not generating any particular data. It is trying to fill in the gaps. So it is, you can say RNNs was one of the steps earlier. LSTMs and RNNs were the initial steps when they were looking at predicting what is the word coming after this particular word. But RNNs did not understand context. So generative AI today is very different from RNN in 2-3 things. Firstly, it is deep neural network, which it uses. The second is the embeddings, the enriched embeddings with the transformer architecture. So today's generative AI is very different. You can say when RNNs came, they came up with the concept that they would enable us to embed and generate information and sentences or words after particular words, or images after particular images, but they cannot. For research purposes, which models are accessible and freely available for image/video? Lot of models. Just carry out a net search. I will share some Medium blogs which I have written, but you can explore Llama. You can explore visual language model of Llama, right? Lava is the visual language model of Lava. And just explore. I'm telling you, just go to ChatGPT and type, you will find the answers there. But we have worked on Llama and Lava very, very often. We have worked on Mistral. We have worked on many other models also, but these two we found to be good. And right now I've homed down to Llama and Lava. Lava for visual language models and Llama, right? And Llama is now come up with Llama 3.3 as well. Okay, any other questions? Thank you. So don't you think generative AI has overpromised too much? I have used it for this thing. Yes. So so any technology which it comes, no, it comes through, there is something called as a Gartner cycle. If you look at the Gartner cycle, the first thing is the technology germinates. Then there is a, you know, height of inflated expectations. Generative AI will do this, ye bhi kar dega, wo bhi kar dega, it will be able to achieve everything. Then suddenly you realize, no, it is not. So now people are saying, yeah, LLM can do it, but we have to be cautious. It is hallucinating. It can generate videos, but those videos you can come to know are inaccurate. It can generate models or diffusion models. If you look at some, you make a block diagram, there'll be small things which you will find, nahi yaar, I cannot use this completely. Number of applications have germinated on the internet wherein they say, I'll make a presentation for you. Certain things are good. Certain things are still in the things of maturity. So you are right, because we are at the peak of inflated expectations. Now there will be a sudden drop, and that is called, that drop, when it will come, will be the trough of disappointment. And then technology will plateau out to a particular place wherein people will realize this is the way this technology needs to be used. So we are somewhere there, and now people are realizing the pitfalls and the problems with generative AI. So you are right. As per people, it has promised, over promised, but with smart people in place, you can use aspects of generative AI very innovatively for application specific requirements, innovatively. So you have to be very clear in your mind and study thoroughly, experiment, and then put those applications in place, and you will be able to achieve. But do not think generative AI can solve all the problems. No, you have to understand, you have to go down to the conceptual level and understand that. Right, ma'am? I think we are done with time. You have to start your next lecture.
Yeah, it
So
has been
thank
a
you very much
very,
for a patient hearing.
yeah, thank you. It has been a very insightful session. You started with the fundamental concepts, and I'm pretty sure the participants who are not aware of the fundamental concepts of AI would have benefited a lot from this session. So we are very grateful to you for joining in today, and we look forward to like your physical visits to our institute as well for future talks. We would be
Or
delighted to
I'll
have
be
you there. Yeah.
right, and I'll be more than happy. And some of the students who want to do internship with IIT Delhi, who are very keen and who feel that they are competent enough to right uh, do something fruitful. I'm sure they're all competent, but those who are very keen, they can approach us. We will take a few students on internship if they are very keen
Okay.
for working in AI applications and generative AI.
Sure,
Thank
sure.
you.
Okay, I'll connect
Thank you, ma'am.
students with you. Thank you so much.
Yeah.
Thank you.
Thank you. Thank you, everyone, for a patient hearing. Thank you.
Okay. Uh, so I think our next speaker, Mr. Sunny Mehmed, has already joined in. We have a couple of minutes. If you want to take a break, we'll start exactly at 7:30. So I think we'll wait for 2 minutes. Dr. Nikunj, you will take over this session.
Yes, madam. I will take over from
I
here.
think Mr. Saneem has already joined. We'll start exactly at 7:30.
Okay. Okay. After a
Yeah.
couple of minutes, we can start. Okay.
Yes. Dr. Nikunj?
Yes, madam. Yes. Okay. Okay, so I need to share my screen over here. Uh, Good evening, everyone. So it is my pleasure to welcome you all to the sixth session of our ATAL 6-day online FDP on data, deep learning for vision and language. For this session, we are privileged to have with us Mr. Saneem Ahmad Chemangut. Hope I pronounce your name correctly, sir. So Mr. Chemangut is currently a principal data scientist at Cellular Technologies Jaipur with over 13 years of experience in AI and related domains. At Syllable, he heads a team of data scientists in creating AI-based products, contact center intelligence, and time series forecasting, to name a few. He has a background in AI research with 15 plus conference papers published in prestigious venues such as NeuroIPS, ACL, NLP, UAI, etc., and 16 US patents. Prior to joining Syllable, he was a data scientist at Microsoft and a research scientist at IBM Research and a master student at ISC Bangalore. Today, we will enlighten us on the topic a brief history of large language models, offering insights into the evolution and impact of this transformative technology. So we are happy to have him here, and so let us welcome Mr. Saneem Jamangut to begin this session. Over to you, sir.
Yeah, yeah. Hi, everyone. I hope I am
Thank you.
audible.
Yes,
Thanks.
you are loud and clear, sir.
Yeah,
Please.
thanks, Nikunja, for that introduction.
Thank you.
I'll share my screen. One
Yes,
second.
please.
Let me see. I think I have to share the screen first. One second. I'm a bit struggling.
No issues, please.
Entire screen. It goes here. Wait. Can you see my screen?
It is coming up.
I think it's
Yes, visible.
Okay. And I'll just put my slide.
Yeah.
Okay, can everyone see
Yes.
my screen slide? Everything clear?
Yes, it is
Yeah.
clear. Okay,
Yeah.
sir.
So I was just messaging Preeti ma'am that doing a session right after Dr. Amit's right. There is going to be a huge overlap. I am going to talk about large language models. He talked about a lot of things, including the large language models. So there is going to be a bit of overlap. I hope it helps you all to remember
Definitely.
more. Maybe, yeah, I'll try to give a different spins. I'll try to, explain things which I am more interested in. One thing we'll try to do is that you can stop me anytime. There are like some of the slides, most of them are placeholders. Any slide you give me, I can talk them for half an hour at least. So that's how I'm going to do. Again, as I mentioned, I'm from I live in Jaipur. I'm from Cellular Technologies. I am originally from Lakshadweep, which is like this tiny islands in the Arabian Sea, and from Kerala. Okay. So what is a brief history of large language models? The name obviously is taken from Steve Hawking's, the book, basically that brief history of time. So large language models have been doing amazing thing, and so it's time that we actually look at their history. Before I go into the history, I'll look at the NLP thing, right? Obviously, large language models, I'm only going to talk about NLP, how the text we take as an input, we do something on it, we get some output, right? Not going to talk about images, videos, nothing else, right? So this is the hello world of NLP, right? Anyone who works on NLP, who reads an NLP textbook, the first hello word kind of you do in programming you look at sentiment analysis, right? It's though it's like sounds very simple, it is heavily used. Everyone wants to use it. Amazon, they want to look at the reviews, YouTube and everyone. So one is sentiment analysis, and that how it's done. A lot of text goes in. You say that it's positive, negative, neutral, something like that, right? So that is basic NLP applications. The other one, which is popular, is the translation. I'm just giving out some explain some tasks which NLP models do as an introduction here. So translation, as we call in NLP, is machine translation, because a machine is doing the translation, not a human. So machine translation is you give an English text, you translate to Hindi or any language A to B, right? So here it's like I'm talking about large language models, and this is what Google translates and give in Hindi. The other one, which is kind of more closer to me, is question answering system. I have worked for like more than 4 years just building question answering systems, way before ChatGPT was a thing, right? So in question answering system, what happens is that you get a question: what is the capital of Germany? You're also given a paragraph, maybe more, and then you're supposed to look at the question and then the context paragraph, as we call it, look at it, find the answer, and then show. In this case, just one word, right? Now. There are a lot of these assorted applications which I showed, right? And then you might be asking, like, what are the importance and where are these used? So I'll just take an example of our product which we created in Syllable, which is being sold across the globe, right? To many of our clients. I wouldn't want to put their names here. So what we do, all of these things which I've shown and some more, is this platform we created called Contact Center Intelligence Platform. Okay, what does it do is that we have a lot of contact centers in India, and we also make a call. I call someone in Amazon. I say that my the thing which I bought is delayed. What should I do? And there is a conversation between the agent and the customer, right? And the agent is trying to solve the issues, or maybe trying to sell something, and the customer is talking. Now, what we did here, and this is like a live running product, is that when this conversation happens, there's a lot of text coming, right, and a lot of audio going back and forth. There is this listener AI system, right, which is this system which keeps looking at what they're talking and trying to suggest and do many things. And this image which you see is the dashboard which the agent sees, right? So we are kind of like helping the agent, like, this is what you told, this is what the person told, this is what you should do, this is what you should not do, something like that. Okay, so in the screen at the top, you can see that there is an overall summary we give. So that is a complex task. What you do, like, for example, a person is talking to another person, agent and customers are talking for 10 minutes, 20 minutes. You get this small summary with it, right? So we have the system which keeps updating the summary. Why is it important? Is like, say suddenly someone is saying that, okay, this call, let me give it to my manager or something, let me escalate to the other person. The other person can quickly see the summary, what's happening till now. Then the other one is that there is this micro summary. It's like if the user keeps talking longer, we give a quick summary of what just that 2 minutes, 3 minutes they talked about. Then there is more, and there's like the sentiment coming, right? Because we really want to understand that if the person is like feeling happy or sad. Maybe the agent will know it, but we are just doing it here because it's also good to keep record, right? Like if there is an agent who is getting a lot of negative sentiments from his or her customer, and then it's good to know for the manager, and they can give some measures to make it better. There are other things like guided script. It's like there is a list of things agent has to do. Are they following it correctly? There is like a knowledge miner, which is like a search engine, but it's not a search engine. What happens is, like, for example, this is like a banking situation, and a person says that, someone has called me and they're talking about their ATM card is not working, right? So the agent doesn't know exactly what to do now. He just goes, and he or she just goes there and types like ATM missing. And then it goes through the whole database of their manuals of contact center, and then finds the answer and then shows it. So that's it. But that's what we call it, like knowledge miner. It's like mining the knowledge out of a database. Then there is this central panel, which we call the suggestions panel, in which it looks at the speech rate of a person. It has like some battle cards, for example, like in very complex situation, what you should do, what you should not do. It detects the rudeness. The person is being too rude, like, please don't be this rude, try to pacify them. And there's this knowledge-based suggester, which is probably the most complex thing we built in the whole system, which basically looks at the whole conversation and try to suggest, right? For example, here you can see this blue thing. that it says that ask the customer this, convey the customer that. So how can you suggest some better actions? So all in all, what I want to show is that these individual NLP tasks which we see and hear, right? They all can come and become these nice products, and it's very useful, and a lot of customers are interested in, and we have already sold it to some of the customers, right? And that's that. And each of these blobs, which you see, they're all AI system, they're all NLP systems. One of the system which I didn't put here in the screen is that obviously the agent and customer is talking in audio. They're like it's audio files, and there is a first system which convert the audio into speech, right? And that system is the beginning part, and that's how the conversation happens. It's like a chatbot of conversation, right? Chatbot view. Okay, so that's what we created, and so we have pretty much looked at all these applications, and I come back to my favorite, which is question answering system. Here, like if you're given a question, if you're given a bigger paragraph, now it's a bit complex than the earlier one which we saw. And there's a question answering system. It looks at these two texts and gets an answer, right? But the major idea here is the latest whatever algorithm everyone uses now. This QA system is like a heavily complex equation, right? There is no if else condition. It's not a proper programming. It's just like a complex equation. All these LLMs, everything is an equation, right? So this size of equation can be in GBs and like tens of GBs or something which is bigger that you can't even put in your in your RAM and all. But at the end of the day, every one of the systems are just complex equations, which has like an exponential log and a lot of matrix multiplications. So like now to think of like, okay, now let me start with the history of large language models. The first question, it would be like how to convert text into meaningful numbers, because obviously all the AI and everything is an equation. Obviously text is not an equation. Text is just some characters and some words in some order. How to convert text into meaningful numbers, and that is the first question we'll start with, and then we'll see how these things answered, and then we get LLM at the end and what we see nowadays, right? So with that, we'll go to the next section, which is like evolution of techniques which created large language model. So we are not exactly at large language model, but we are at the techniques to start with. One thing is that like if there is any questions, you can always ask. I'll just see if there is a better way I can see. I'm not sure because I'm sharing the screen. I'm not able to see anything else. Yeah, is there any question? Otherwise, okay. Otherwise, I'll continue. Okay, so one of the first thing is that obviously the paragraphs we can't put exactly into equations, so we convert paragraph into words. Like we look at each word, and then words becomes the vectors, right? And this is something which Dr. Amit also explained, which is this word to vec, and this is the paper which came in 2013. From now on, in the slides, you would often see the years here because it's going to be the history, and then you will see like where each of these ideas came. So in 2013. There was this paper by Miklo, and specifically it's Google paper, and they figured out that you can look at this lot of text and create vectors for each of these words, right? And these words somehow captures the information. And how are this training happen? Like Amit had in a very high level he has explained, but essentially the idea is that given the words around word in the middle, like you train a model to predict the word in the middle, right? So because the trouble in general, you'll see in the LLMs and in general everywhere, is that we don't have a training data, right? The trouble is that like when we want to create a training data, you need to put a person, they'll annotate some, this is the question, this is the answer, this is the question, this is the answer. That is a humongous effort, and it's very expensive, and it's also very time taking. So biggest things which we observe in the success of LLMs or in the AI generally is that we are able to create tasks which doesn't need any annotation. It can just take any random text. If you have a textbook available, you just put it and it will create a word to vec for it. But by doing that, just looking at text without even any labeling, no one is saying that this like man is an animal, or like a woman is the female of that animal. There's nothing like that. It's just that you just put these words, and somehow these algorithms are able to capture these things. It just worked like a magic, and So the way it worked is that like when you use this algorithm and train a model, and they train the model mostly on Wikidata and in general text data back then. So 2013 is that we didn't have a lot of data, public data as well as. So they use those text and then train the model essentially about missing words. Can I use a model to predict the missing word? And in my prediction model, there is somewhere a vector being generated forward. And one of the things we observed is like obviously that man minus woman, the distance between the vector distance between them is very similar to king minus queen. And I suppose it would also be very similar to bull minus cow, right? And we got this, and I remember like I think probably it was 2014 or something. We got this Python library, and we were all like, oh, this is nice, and this like word this correlation somehow able to identify. And the paper was talking, the example which I show here is essentially what paper and blocks were talking about back then. So walking, walked, swimming, swam, that kind of relationship it was able to capture. The way it's capturing is that you just subtract, say for example, Madrid from Spain, and then just see like what word is closest if I do Italy minus dash. What is closest to Madrid minus Spain, right? So that will become rho. The idea is that vector distance in that space was giving me the information. The absolute value of the vector, it's kind of pointless. It doesn't mean much. But when you look at the pairs and their distance, it kind of was giving an information. And one of the things, which magical happened, or which I felt personally magical, was that we were looking at like, if I do Sachin Tendulkar minus football, Sachin Tendulkar minus cricket, and then I put like tennis, and I see that who will be the similar to Sachin in tennis, and then it was actually giving me Federer. Right, and I suppose no one else had tried those combinations, or it's a rare combination. So the people or the algorithm which was trained to identify these patterns, and the patterns were coming which no one even expected, right? Because like that's where the word embeddings and the meanings were going beyond what we were expecting, and now we can see LLMs doing everything what we can't even think about, right? So that's I felt like it's the beginning of all this deep learning magic or this LLM magic here. Now, okay, so we have a vector for every word. And how many words are there in English dictionary? There are like plenty, right? A huge number of vectors. And if you take Oxford Dictionary, there are many. And now the question is, Oxford Dictionary is common words, but what about the proper noun, which is like a place name? What about Jaipur? Like, does Jaipur get a vector? Then if Jaipur gets a vector, does every city in the world gets a vector? How many cities are there in the world, right? And how many people are there? Do their names get a vector? So there is an issue that you can't give everyone a vector, right? And it's like just exhaustive, and you can't train on everything. So then people are like, okay, let's not do every word get a vector. Maybe we'll start, like splitting words into smaller pieces, right? So if there are like words which are common, let them get vectors. For example, if the is a very common word, let them get a vector. But if there is like a something like a rock star, let's not give rockstar a word. It's not a very common word. Maybe rock gets like a vector, and then tar get another vector. So that's where people figured out that let's do splitting, and then maybe the splits get vectors and not the full ones, right? And how do you split is kind of the algorithm which this animation is showing the screen. I don't want to go into the details. There are like many things to cover later. So what happens then is that if I have like a sentence, you have to read this slide from bottom to top and not to top to bottom. So if I have a sentence like a visually stunning rumination on love, right? A visually gets like each of these gets separated as like each vector, but rumination apparently is a very like a rare word, so it gets like split as rum and ination, right? And then on and love gets this the same way. So that's how it works. Like there is a rarer word, it gets split, and that is how all the LLMs work. They all have a limited vocabulary. Even the best and latest every word, right? They don't have that kind of like what we call this tokenizer vocabulary. Now, for example, right? If I have to show OpenAI, right? GPT-4o, GPT-4o mini, these are the latest ones, right? And you can see here that so if I'm saying, hey, I'm giving a talk at Jaipur. अरे मैं जयपुर में एक I'm not that great in Hindi, so let's skip that part. दे रहा हूँ, right? So what happens is that you can see the way the tokenizing happens. So hey gets a word, I gets a word. These colors are essentially saying how is the word split. But Jaipur in English gets a word, but Jaipur in Hindi is essentially split as J and Pur. Like you can see that two words, right? And obviously Vyakyan also gets split terribly. So this is how the general what we call the the word splitting happens. And now the good thing is that obviously we have a good coverage. Like a word might be split into 4 or 5 in the worst cases, but we are still able to get some embeddings for it. Okay, so we have words, we have kind of covered, everyone has vectors, we kind of understand what words are. But now the question is that, like, can we get an understanding of whole text, right? Obviously, the text, like word alone, doesn't make sense. And Dr. Amit gave an example of bank as the what we call is homonyms, where one word has multiple meanings. So if you look at a full sentence, then how do we represent it? What is a good way to like model a full sentence in equations, right? The major issue here with full sentences is that the size of sentences are not limited. I can say that hi, it's a sentence. I can give a huge monologue about like world and word politics or whatever. That is also one input. So there should be a what that called changing size of input. I should have an equation which can take a change in size of input. And that was the biggest issue people faced while working with NLP at the beginning, right? How can I have an equation which can take one word also as an input and maybe produce an output? For example, say sentiment analysis. Someone wrote a review of like great, just one word, and sentiment is positive. But the other guy wrote like very detailed about how they attracted and how the music was, how the cinematography was, and that also needs to be go into the same equation and say positive or negative. Now the solution to this was what we call this RNNs and LSTMs, right? So RNNs essentially was that, oh, let's not take word one by one. Let's do rather than taking word all together, let's take words and have the system where each word go one by one and create an embedding, like or some equation at the end which can somehow capture all the sentences. And the major issue here was that when you have really long sentence, your first word goes in. For example, in this case, what is the second most abundant element? If you what goes in, and then like equation happens, some one output of equation goes into the equation again, which is like because this loop is goes in, it goes on, and then the trouble was that when the sentence becomes longer, it only kind of remembers the last word because the first word went, then a lot of processing already happened. So then came LSTMs because it had some memory and stuff. So I don't want to go there. And you keep a track of the dates at the top, right? So RNNs were introduced in 1982. It's older than me, of course. And 1997 is when LSTM came. And then one of the question was that, oh, what about like you took the input? What about output, right? So can we also have outputs from these systems? And that's when then RNN or LSTM also had this decoder thing, as we call it. So for example, if you put a lot of words as an input, and then there is this another system who outputs words, right? It's like you can essentially consider that outputting a word is a classification problem, right? So if there is a vocabulary of 100,000 words, so it's a 100,000 classification. Every time my model is doing a 100,000 class classifier, and it says that, oh, the next word is the, then it is car, is moving on. So it's like then the same kind of system works, and it keeps generating word as an output. Okay, the trouble here was that in this particular case, okay, it's a translation one, you can see. I don't know which language it is, but this com bite is being translated to English at the top. So it says that please come here, right? So the trouble is that the whole sentence here gets kind of bottlenecked on this C thing, which is what we call this context vector from the input. And because of it, some of the longer sentences and all had issues of this translation, this model. So then the question was that, okay, this kind of this information bottleneck we have to reduce. So like, is there something else we can do? And that's kind of where the neural attention models and the whole magic of transformers started, right? And I'm going to show one image here, and trying to like motivate what an attention here is, right? So this is like a picture of a cockpit and on an airplane, and someone's probably landing or taking off. So if you're a airplane pilot, you have like humongous number of graphs and like meters and running, and there are a lot of buttons, right? But if you're probably taking off, you don't have to look at all these hundreds of buttons, right? You have to just focus on maybe these things are the important ones now because I'm taking off. These things probably I have to take care when this happens, that happens, right? So the idea here is that only like focus only on the important things at hand now. What is needed now, just focus on it. like the co-pilot, sorry, like the pilot does on an airplane, let our model also focus on the things which are important now. It will make sense in the next page. So what happens here is that, right, when it's trying to predict each word at a time, for example, I'm predicting please at a time, let me not just look at the C, but let me also look at each of the inputs which I had before. So com bit her, I'm supposing com means please. So right, if it's generating please word now, maybe at that time it can focus on com. Then if it is generating come, maybe sorry, com would be like come. I suppose bit might be please. So it's supposed to focus at bit and then whatever the corresponding words are. So it's supposed to just attend on what word is useful at that moment, right? How do we know which word to attend when we are decoding? Obviously, the trick is that let us have yet another ML model to do it, right? So let us have a small equation, small model, which at the given point of time will take a call of which input should I focus now, right? And so, for example, here this is a Chinese to English translation. So there is like a encoder is going, it's going, creating all the LSTM kind of embeddings. But now in the decoder, what happens is that like this dark graphs you see, they're essentially saying that which letters or which characters in Chinese is what it focused at every time it was producing that English letter, right? You can see this. So this is the attention thing. And how do we know when to attend? Let's have yet another model, ML model to do it, and let's train that as well. So this is how it looks like. An attention mechanism model happens, and then it focuses on the input. Okay. So yeah. So any questions? Anything on it? I might go in more like very much detail. Should I push and talk about more latest things? That's also possible. So Preeti ma'am or Nikunja, like if there is, if this is becoming too basic, I can skip and go to the latest ones as well.
No, sir. The basics are very much fine, and
Yes.
your pace is also very nice. So you continue with that. No issue, sir.
Oh yeah. Thanks. Okay. So this is the encoder decoder with attention, and this came up like as I put this paper 2015 paper. It was essentially used for translation. No one else was using, to be honest, attention. It became like a big thing, and like a lot of people were working. Like I had this my roommate who was working on attention back then, right? And then what happened is this 2017, obviously, like I suppose maybe many people in these sessions might have talked about this paper called Attention is All You Need. I essentially call it attention on steroids because attention was there. This paper, Attention is All You Need, is saying that like you have these LSTMs and you're looking at attention and what should I use? Forget about LSTMs. Just let us just use attention everywhere. And that's the whole reason the name is Attention is All You Need. Because till then people are just using attention as like a small block in your model. Like I showed last page, right? It was just this small blue block in your big model, right? Now it is just use it everywhere. Before I say why it was successful and all, right? Let me tell one of the issues we had with these LSTMs and this RNN kind of model. Obviously, there was this memory thing. Attention was kind of trying to solve it, but it was there. But another big issue was that training was slow. Why was training slow is that because you had to send every word once to this model, right? This encoder and RNN, for example, if I have like a big paragraph, say 1,000 words, 100 words, or 500 words, I had to give that input, get some representation, then put the next word. So training was terribly slow. I remember we used to train model, it used to run for like hours and days just to get a small task doing, right? Not like LLMs do nowadays. So that was one of the bottlenecks, right? You're not using the full power of GPUs or anything because you're just sending one word at a time. One thing which this Attention is All You Need, or what this call as transformers solved, was that they were like, no, let's not have LSTMs and RNN, so there is no sequence here. You just put all the words together and just push them all parallelly. So all these words are processed parallelly. You put all the words together into these equations, they go here, and there is this self-attention layer. What is self-attention layer is like earlier in translation, the output was kind of attending to the input, right? Like the English word generator was attending to that whatever language word was. But in self-attention, the idea is that you don't have to attend to anyone else, you just attend to yourself. Let the words attend to each other, right? So the example which Dr. Amit gave was about the bank, right? So if there is like a money plus bank and there is a fish plus bank, right? Then somewhere the bank is going to attend to the fish part in one of these layers, and that's going to somehow make the model understand, oh, the bank what I'm talking about is the river bank and not the one which is related to money. So that the trick was self-attention layers. And for example, this is one of the examples of kind of motivating what self-attention layers are. You have a sentence like, the animal didn't cross the street because it was too tired, right? This is a classic NLP problem, saying that how do you understand what this it is referring to, right? The animal didn't cross the street because it was too tired. So it is like, is the street tired? Is the animal tired? I mean, obviously street is not tired, but here it is a little more obvious. But the idea here with self-attention is that in one of these layers, in this word, right, this it is attending more to the animal here, right? And then the next version, so it's all layers of because deep learning, right? So you have seen this neural networks, they process the input, you get it like one version of output, and then you process the input again through another layer, and they keep refined, right? CNN, RNNs, everyone, essentially all of them are these deep layers. The reason deep neural network is because these layers were making much more deeper, like many layers, more deep and deep learning. So in this case, what happens is that in the next round of representation of it, right here, because the word to similar representation is happening every layer, like what we are seeing here. There is a word, green is a vector representation of what it goes through self-attention, it becomes the next layer of it. So the way it goes to the next layer, it has attended already to the animal there, so which means that its word representation has some information of the animal there, and that's how it captures those information. Self-attention is the play there. Exactly how it's happening, why it's happening, to be honest, no one in the world knows, because these equations are so complex for anyone to read and understand. But this is the intuition we all have. Now this is these are some images taken from J. Alamar's explanation of transformers. I would rather suggest that you go through them directly than what I explain. If time permits, I'll come back and explain how the attention happens. On a high level, it's basically that there is a vector for every word. So here, let me take it from here. So it has a vector, and the animal, everyone has a set of vectors. Basically, these vectors, you just multiply it together and do some similarity measurement and say that is it more closer to the animal, or it is closer to, say, cross or the street. Right. So there are three types of kind of vectors which is created. One is called query, and one is key, and one is value. And how do you make query? Obviously, you only have one vector for every word. So you have some manipulation, matrix manipulation. You do on a vector, you get query vector. There's another matrix you multiply, you get a key vector. Now, if the query of key, it is much closer to the, or it is much closer to the value or the key of animal. That's how it shows the similarity of the attention. I'll come back to it, if we have time. There is also a softmax here. Why softmax there? We all know that softmax, whenever you put it, becomes a distribution. Everything is greater than 0, and it's all sum to 1, right? The attention, we can't just attention is essentially a distribution on the input. So that's why it's softmax. You give weight 0.2, 0.1, 0.3, and then they all sum to 1. So that's what the self-attention does. Now there is a multi-headed self-attention. That's all again from the same paper 2017. They're saying that one set of attention is not enough. Let's have 7 type of attentions, right? They are all parallelly doing some different types of attention. The high-level intuition here is that maybe one type of attention gives you a peculiar way of information and connecting words. Maybe the next way attention will find some other connections. So that's why it's called multi-headed self-attention. Now what happens is that once you have this self-attention, and the output and input are essentially still the same. So you have thinking a word, it goes through self-attention, all these complex things which happen. You get another vector, you have some small feed-forward networks, you get the R1 output, and that becomes a block. This is called a transformer block. And then you just tag the blocks, right? So this is a green block, encoder block, and decoder block. They're not very different, but you just keep stacking the block, like how you have deep learning networks, layers of neural network. You just keep stacking the block, and that's how you make the model bigger. You might be thinking why should I have a bigger model? So that's what we'll see later. But the essentially idea is that before deep learning, the general understanding was, if you have less data, have smaller model. If you have bigger data, you have bigger model, right? What we understood with LLMs and deep learning models is that this model is not just understanding language, it's also kind of keeping track of world knowledge, right? For example, if you go to ChatGPT now, you ask like, who's the Prime Minister of India? It will, with great accuracy say it's Narendra Modi, right? It's able to do that because somewhere in those giant equations in ChatGPT, in Claude, whatever LLM, somewhere in those numbers, in those equations, there is Narendra Modi written in some weird form which none of us can understand, and it's also somehow connected to PM of India. So if you want your model to capture a lot of information, your model has to be as big. So the idea here is you have encoders and you just stack them up. The bigger you stack, there is more parameters, more places you can store more and more information when you train the model. Okay, so here this is like a translation. There is a "Hey, suis a student." It's like a French. We say that I am a student. It goes through the encoder. At the end, I again get the vectors per the word here, or per the word token here, because word can be split into multiple. We already saw that. And in the decoder, it goes in and it again creates that I am a student. It's a very similar structure. It's just that now there is an attention across also. Okay, so that is transformers. One of the things which we missed was that when we put all the words together and we are doing attention, though we have put like the words here in some order, the equation doesn't care about the order. There is nothing in the equation, the model, which was really talking about which word came before and after. So there is, what about the order of the word? We need to deal with orders of the word. Somehow that information has to go into the model. One of the cases that say, like, if I have a summary and I have to do a sentiment analysis, it said that the movie was good, not at all bad. Now, if you look at the words all separately, there is good, there is bad, there is all, there is movie, right? So good and bad, they are all there. And my model would say, like, I think this person is neutral, right? So the order is what we say that, okay, bad is for not and good is for movie. Right. So how do we give order? One of the reason LSTMs we used to send word by word as an input was because it was capturing that order. Here we are not doing, we are sending all together. So we don't have order. So we add something called as positional encoding. It's yet another vector which you just add to the input embedding words. Like you can assume this embedding is word to vec for every word. You just add it. One would assume it's for appending, but like you just add these vectors and it just works. Right, it's yet another magic thing which works. What are position encodings? How do you create it? There are some sinusoidal equations which people have tried and it seems to be working fine, and everyone just uses it and it seems to be fine. The major idea is that positional encodings are vectors which depend on location of token in text, right? So for example, any sentence, the T1 position will have the same vector, T2 will have different, T3 will have different. Okay. So the whole pipeline, how does it go? You have these vectors. You have these words in French. Every word gets a vector, but word to word kind of embedding. It becomes this yellow thing by adding the position encoder. It goes through the encoders. You get these more informative blue vectors per word, and then obviously decoder starts. At the end, as we all know, it is still a multi-class classification problem, linear plus softmax. Okay, so this is the kind of the story of the whole. Go in detail, but it's going to be a bit dry. But let me just try to explain the programming part first, right? There is like one of the major developments in the whole field of AI was this auto differentiation. So back in 2011, when I was doing AI course in ISC Bangalore, right? What we used to do is that we have to train, say, SVM or one of the small models. You have to invent a new model. You would write the equation, and then you have to manually do, like, with pen and paper. You do the gradient, and then you also feed into some optimizer. Then it does optimization, right? And that was a bigger issue. But now these models, you can see that I'm just adding matrices and plays like softmax and root d cube, whatever way, like people just keep adding. And the reason they are able to do it is because there are softwares nowadays which can just look at this type of equation and just differentiate by itself. Why do you want to differentiate? Is because the optimization, I hope someone has already talked about gradient descent and everything, right? The whole training of pretty much every ML model what we see nowadays is using gradient descent, right? So auto differentiation is needed because differentiation or the gradient are essentially the same thing, right? So gradient, if you want to calculate nowadays, you don't have to think about how, like if x square becomes 2x or x cube becomes 3x square. Nothing, it just is calculated by itself automatically. So the libraries which helps you write all this is PyTorch. So PyTorch, you can put any layers. You just put like this equation, this equation, this equation. You just put it. It will do the training and everything by itself. But if you want to do all of this yourself, you should use Hugging Face. Why PyTorch is a bit more bottom layer? You'll have to write a lot of code. But Hugging Face is a software, amazing library built on top of this PyTorch, which has most of these codes and everything written already. So you can use Hugging Face library, import it, look at this equation, look at how the attention is working. Maybe take a small model, train it on your small data and everything. Does that answer the question? The transform.
Yes, I guess so.
Yes.
So Suchita Arora, Dr. Bhargavi, is it enough or any?
Yeah, I can.
Yes, sir. You can go ahead with your presentation. So if the participant have any other queries, so they may ask.
Yes. Yeah, please ask, and please stop me in the middle, okay? See, I
Okay.
keep going on a monologue. It doesn't sound great, right?
Uh,
One thing
yes.
is, so obviously you have to look for a PyTorch and Hugging Face. I mean, historically there are a lot of things. When we started, I think there was something called as Tiano, and there was something called as Torch, Lesani, Keras, and a lot of people created libraries back in 2015, 2014 around. A lot of them didn't succeed. So PyTorch and TensorFlow by Google and PyTorch started by Facebook are the ones which are the best. And Hugging Face is the best for transformers. So Hugging Face is like layer on top of PyTorch. There are like really nice small blocks and codes you can start doing it. Okay, transformers. I'll do one thing. I'll keep it separate now. But if we have time, we'll come back to it. Okay, I want to talk about large language models where we are beginning. So before I get into large language models, right, we have to first understand what is language model, right? So large is just a class of language model which are just huge, bigger. So language model essentially is that it can understand language. It can say that if you write a sentence, the next word what it is, like if you can say that, it kind of means that you understand language. That's why it's called language model. It's able to model a language, right? So large language models, like language models have been there for a while. There is this nice small library called CanLM, which is nothing to do with transformers, LSTMs, RNN, nothing, right? But large language models is what changed the game, and so the biggest one is the GPT. So these are what OpenAI came up with in 2018. Like back then it was called GPT, but now it's called GPT-1, the first, right? It was called the decoder only model. So we saw that architecture before, it had like encoders and decoders. Here it's just the decoders. And from now on, right, I'm not going to much go into details of the equations. They change very little. They don't change a lot. Some tricks and tips come in, but essentially now it's going to be the size of the model and the training data and the ways people deal with it, right? It's now all about like who has the biggest computer and who has the biggest data. They can create bigger models and better models. Okay, so the GPT, the first. So GPT had like this amazing pre-training. So let me just explain one part probably which I missed is this pre-training part, right? One of the things which we also used to do in LSTMs and RN and everything, and even including transformers, is that till then we always used to have a task. For example, I want to do sentiment analysis. I want to answer a question, right? So we used to have a small data set, say like 100, like 10,000 input, 10,000 output. You take a small model, you train the model on those 10,000 input and output. You split obviously into train and test and look at test accuracy. It's like whatever, 80, 50, whatever, right? So that's how it used to happen. But later people realize that that's not what you should do. And that's kind of, although the big thing about deep learning is that you should not train your model on the small data, because when you do it, you can't have the model big, right? Because if you take big model and small data, it's going to overfit. And that we have seen in the basics of ML. What we need is that we need a model which is already pre-trained on some task. It is unrelated to what you're going to do next. Obviously, it has some relation, but the idea is that you need to create some task where your model can train on doing that task, and then you do a transfer learning. Why is it called transfer? Because it's doing some task A. Now I'm like, no, you train well on task A. Now let's just fine tune on small of this task. Let's train a bit more on my task which I'm interested in, right? So that's why it's called pre-training and fine tuning. And the idea was that, okay, which the dummy task I have to do is like the task has to be something really related to language, so that my model already understand language by doing it. Is it useful? Probably it's not, but it understands the language. And when the thing which folks figured out is that predicting next word, if that is a task we can do, and we can train a model. So you can take any textbook, just go take the wiki dump, any page, any website in the world, just take it. It has a sentence, take the first 3 words, try to predict the 4th word. So that is an input output already for you. You don't need anyone to annotate, nothing. So you just have this huge data, right? Which has like input is 4 words, output is 1 word, input is the next 5 words, output is 6th word. You keep creating those pairs. You just train this generative pre-trained model. Whatever transformers we discussed, just train this model to predict the next word. And what we observed, and this magical thing is that by the time it just keeps predicting next word, it was able to understand the language, it was able to understand the grammar, it was able to understand information, it's able to understand that. For example, in this case, right, student opened there and dash. That is the task we were trying to do. And we are expecting the model would say that books or laptops or exams or minds, right? And that's kind of the model is able to connect the student open to books and laptops. So it's able to connect many words, it's able to make some like world knowledge and world models inside it. But is this very useful thing? It's not really not. Like no one is going to use a model and say that, okay, I have the sentence, fill it for me. That's not useful, right? So what we used to do back then is that you have a model which is pre-trained on a lot of data. Now you just take it, the model is huge, you just fine-tune it on small data. So now the fine-tuning can work, and because it already knows language, it works amazingly well. And this was a huge paradigm shift in deep learning, right? And now the question was that, does everyone have data and resources to train this model on this huge data and everything? Not really. So then what happened? Hugging Face became this amazing platform that all this pre-trained model on this generic data, people would like people or companies would just train this model, spend millions of dollars or hundreds of thousands of dollars, train it, and just freely put it in Hugging Face. You can just take that model, just download the model, put in your laptop, take some small data, train it, and it was working amazing. It was working better than any other model which we created. So this idea of this pre-training to get the model trained on some generic knowledge and then fine-tune, right? That became this amazing trick throughout, and that just worked. Okay, so the whole idea was the dummy supervised task. GPT guys were always, the OpenAI guys were always focusing on let's predict the next word, and that's enough to get all the information. One thing is that why is it called language modeling? Because it's trying to predict next word, it's trying to model the language. That hence the name. Have you seen this next word prediction anywhere else other than GPT and AI? You all have. Where do you see it? In your lap, in your mobiles and everything. Whenever you type, right, it shows the next word. So it is already kind of modeling you, right? It's already have a small kind of language model there. Is it as good as GPT? Probably not, because it has to fit in a mobile. So for example, right, if this is like a screenshot of say my mobile, I am putting like thou shalt, and it says that next word you're probably looking for is not, right? Like thou shalt not is like this kind of 10 commandments, right? In the Bible, there are like a lot of this, thou shalt not kill, whatever, right? So that kind of thing happens, and the language modeling is already there. Now the one in your mobile can do a bit of things, but the GPT can do like many of the things. One other part of this language modeling, which is the next word prediction, is that you can start just keep blabbering, right? You can just put next word. For example, the student open their books and just picking books now. Now give me the next word and then put that word, next word, put that word, and keep running the same algorithm to create next word, next word, next word. You have like stories and songs and poems, whatever you can just keep creating. So that became that like kind of a generative AI and the generating text, and that became a big thing, right? You're essentially having classification model, it just keeps whatever the output is, just put it as an input and then generate the next one. Okay, so
Excuse me, sir.
yeah, there's
Excuse
a
me,
question. Is it?
sir.
Sorry.
Sir, there is a
Yes, sir.
question from Dr. Bhargavi. So he's saying, sir, how is pre-training different from transfer learning?
No. So transfer learning is the paradigm. In transfer learning, you do first pre-training and then fine-tuning. So it's essentially the same thing. You understand? So transfer learning need not be always pre-training and fine-tuning. Transfer learning is like a name which you tell that I have a model which I trained on something. Now let me use it for something else. It need not be, for example, right? You have a model which is trained to an image model. Okay, it's trained to detect English characters, right? Now I can use that model and fine tune to detect Hindi characters also. So there is a transfer learning, but training to detect English characters A to Z, that's not a pre-training model, right? It is a proper training data you're given. You put a photo of A, you say that it's A, and you take B. But here pre-training generally is like you do it on a huge data and you do it on a very related task. So you're right. Transfer learning and pre-training is like essentially like the same paradigm. Transfer learning is what you call in general. The steps of transfer learning is pre-training and then fine-tune. I hope
There
that
is
answers.
there is another query
Yes.
from the participant. He's asking, Dr. Miranda is asking, I have trained a visual question answering model on smaller
Yes.
OQ BQA dataset using VIT GPT-2, and
Yes.
he got the accuracy around 99%.
Yes.
Always the accuracy is 99%, he's saying. Predict the answers correctly even if I upload a new image. Is the high accuracy because of the overfitting of the LLM that used, which can predict correct answer?
I'm not sure. So generally, if you see 99% accuracy, more often than not, there is some issue with the way
And
testing has
he's
been done.
getting always getting that 99% accuracy. Even
There
he,
could be. So one thing is that you can
yeah.
probably check. There is a good chance that there is an error in the
And he's asking,
testing.
is there any overfitting of the LLM?
No,
That is,
overfitting, so LLMs generally what we do, we don't have much of an overfitting because of this pre-training and fine-tuning. But some cases, like if you're taking a LLM from the online and just downloading and using it, there is probably not a overfitting because they have made sure it's not there. When you fine-tune it at your end and you run it for a longer time, there is a good chance of overfitting. It can happen, right? So see, like this ML and AI people have this fancy way of naming things. So there is this thing called as catastrophic forgetting, which essentially says that you have a pre-trained model, it's on some task, you take it on a new data and fine tune, it is going to forget what was trained before. Like fancy name is that you put catastrophic as a term here. So catastrophic, so that can also happen when you do a bit more of fine tuning. So then you have to be like put learning rate very small. You have to keep your like maybe only fine tune some layers, and nowadays. One of the idea of fine tuning is that you don't fine tune the whole model, you fine tune what you call these adapters, right, which are like essentially a small equation you attach on top of the LLM layers. And so the LLM layer stays the same, but you have the small equations around it which can alter it. So there is something called as low rank adapters, which is very famous nowadays. Yes, so there is a good chance the experiment setup has some issues. Is there any other question? I'll also rush a bit, sorry
there
for a
is
bit.
one question is that what accuracy is considered as acceptable if not 99%?
So 99% is obviously the accuracy. It's very much acceptable, right? It is it's best. What I'm saying is that in my career of doing AI for this long, whenever I've seen 99% accuracy, it's more often than not there is a mistake, right? It's like there is a mistake in evaluating. Like maybe there is an evaluation script has a mistake or something like that.
Yes.
But 99% obviously is an accuracy. It's amazing. Like if you're verified that all your codes or everything is right, there is no leakage. That is one of the thing happens, right? There's the label somehow comes inside your input data. It used to happen in like time series processing and tabular data. Maybe it's performing well. Yeah. But 99 is obviously the like amazing. And what is an accepted accuracy, to be honest, is not a AI question. It is more of a business question, right? For example, if I'm creating a chatbot, right, and the chatbot is going to be used for very like severe tasks. If a decision has been taken on the chatbot, someone like a big like issues that can happen, then the accuracy is very important there. I need to have 95% accuracy. But if just chatbot is something which I give to kids and they can make some poems and stories, then I don't need accuracy at all because it's not going to hurt. So what accuracy you need is very much a business problem. In Sellable, we work with a lot of clients, a lot of problems, and the accuracy, what they demand and what we are able to provide, changes a lot according to domains and everything. Banking guys, probably they need more. Others, probably not. Okay, I'll just rush through. Just give me 5 minutes and then I'll come back to the question. So BERT is BERT is another famous one. GPT, it came around the same year. One of the things was that it had these 12 layers, which is like now you can kind of start looking at this thing called as parameters, right? It kind of tells you the size of equations. So 110 million parameters, like was the first time we have seen any model of that size. Right, like earlier, all the ML model used to be in some maybe MBs or KBs. Now it's going to the hundreds of MBs, right? Everyone's like, oh, this model is huge, but it was also great. How was it pre-trained? Now you can see that it was pre-trained on this data called book corpus. It has 800 million words. English Wikipedia, you just take the whole Wikipedia and just download and train on it, right? So that is BERT. There is BERT base, which is small. There is BERT large, which is big. What happens in large, the number of layers increases. The architecture, everything is exactly the same. Then came GPT-2, and that was the next year, 2018, 2019, right? In that, again, what happened? Bigger model, bigger data. That's it. Like whatever was in GPT-1, GPT-2 is bigger model. The number of layers just went more and more. We have got 48 layers of GPT. The size for the first time went above 1 GB. It became 1.5 GB, right? That's the model size. GPT-2 no one uses nowadays, but yeah. And it was trained on 40 GB of web data. Now see, like people are started looking at web data. Till now, it's all book corpus, Wikipedia. No, now like any web data. How did they do it? They use Reddit and also that's not very important here. But they used the 40 GB of data to train the model. And one of the funny things which happened back in 2019 when the GPT-2 came out was that they showed that using GPT-2, right, they were able to write these stories, like especially this one about a scientist inventing unicorn, and everyone was like, everyone who was working or researching in AI just blew our mind. We were like, wow, like how is this able to create such a realistic kind of story? And this is the first time it happened back in GPT-2. And then OpenAI had their own drama. They told that, oh, GPT-2 is so good and we can't even give it to anyone to use because it's so it's not good, like AI is so vulnerable, it might have some issues, let's not we want to hide our GPT-2, the usual drama in business. So that happened, and this was like a very pivotal moment in the LLMs, and everyone's attention went to, oh, GPT-2 is amazing. Okay, and everything with GPT-2 wrote, like this was this prompt. Basically, someone wrote this sentence and told that keep filling next word, and that's how this whole story was generated, and it was very, very meaningful. And now on the sides in 2019, again, Google was working on this T5. It's a model which I have also used in a couple of my papers as well. Is that here the training happened on 750 GB. Everyone is like, okay, let me try to put more and more data, right? And they have models now in 11 billion parameters. Let's say it's around 10 GB or more. So the model size is increasing. They had a bit different of, rather than predicting next word, they were predicting the words missing in the middle. There are good and bad about doing it. One of the things it could do was that you could kind of give a task at the beginning and ask it, and it used to be able to do it. So now this is where the small idea of one model doing multiple tasks coming up. Till 2019, it wasn't a thing. We were creating different models for each of the tasks. Now it's kind of becoming one model to do all the tasks kind of thing, right? So there was this T5, and we could just give a small input saying that, okay, now your task is summarize, give a sentence, and it used to do the summarization. Now we say that, okay, translate English to German, give a sentence, it used to translate. So that used to happen, T5. Then came 2020 and GPT-3, and again, bigger model and bigger data. The number of tokens and data is like humongous. Common control vectors, like the data just went huge. The model parameter also went huge. It's like 175 billion parameters. It's close to 200 GB model, right? And the last line is also something we have to keep track, which is that $4.5 million of compute was for just for the compute, right? For the GPUs, how much they used, this many millions of dollars were used. Now the money game and the data game and the compute game is starting coming in. One of the things which happened in GPT-3 was that it could do in-context learning, which means that you can try to give a direction, because it had seen a lot of models and everything, that you can give a direction, it started learning from it, right? You can say that translate English to French, and then you give anything and starts translating. Then you could also give few shots, which means that in the input itself you say that, by the way, if someone asks A, I give B. Now look at this example and learn and do your task. So one shot and few shots started coming. This is a very famous paper. Large language models are all few shot learners. So that became a thing in GPT-3. So there are a lot of other models which came till 2021. Another thing which happened is this instant GPT, which is like, till whatever we are doing still was that we were just telling that, give us a text and just predict next word, right? Rather than that, people are like, no, I don't want like the GPT to just fill my next words, but I want GPT to do what I want it to do. Right? If I ask like hi, it has to say hi, like tell me this, and it has to tell that, rather than tell me this and just keep predicting next words. That's when Instant GPT came. It was again in 2022. So like a lot of happening in those 2-3 years. The idea was that, okay, you train the model on predicting next word. Now let me create a small refined data in which I say that no, don't predict next word, but predict me that if I give this question, tell this answer now. So now that a training data is coming. Till then, there was no training data. You're just training on the input output data. Like there's no unsupervised data. Now there is input and output pairs coming in. And why is it called Instant GPT? Because we were telling that if I give this instruction, you're supposed to do this. If I give this instruction, you're supposed to do this. These 3 lines are a complex way of how to create a small instruction data and use it the best form. I'm not going to the details. Okay, so that's Instant GPT. Then once the Instant GPT happened, and then came the Chat GPT, right? And Chat GPT, or also known as GPT 3.5, right? And then GPT 3.5, again, bigger model, better model. It also went through the instruction fine tuning. So what happens? Like I can write a great ending lines to talk on language model. It started giving. I hope all of you are using GPT 3.5 and GPT 4 and 4.0 now, right? So this is how till 2022. Yeah, any questions still here before I go into the add-ons of GPT? I can go into these details if you have time, but the high-level idea I think you can take in small talk is that there is this instruction set which people use now. There is a huge unsupervised data and a small instruction set, and that instruction set is also very useful, which says that this input should give this output. Yes, sir. Any question?
Sir, there is one question from Dr. Sipra. Sir, there is black box AI. Some told that black box AI accuracy is more than ChatGPT. Is this is there any difference?
I don't know black box. I don't know if there is a black box AI is a model. I haven't seen this. Generally, what we say is black box is essentially. Yeah, I'm terribly sorry. I don't know this. Black box is when we say we don't see what is inside, right? So obviously, ChatGPT is a black box AI because we don't know what's happening. We just use a HTTP call, REST API call, and you get the answer. So that is a black box. Even to be honest, even the Llama model or something which you can download and put in your laptop, there also you can see all equations, you can see how the input goes in and how the output comes, but you still can't understand why it's happening. Another point I wanted to say before I go there, while I just talked about Llama, is that some of these models actually you can download on your laptop. There is a library called OLLAMA, OLLAMA, which you can install. People install OLLAMA. There's not much of an effort, and you can have your model running on your laptop. The good thing is that you don't have to pay for it. You don't need API connection. Someone tweeted when OLLAMA were released, someone was tweeting that they were on some flight. There is no internet in flight. There is nothing in flight. The person was doing some work at office and he wanted some information to create a slide. He just used this OLLAMA, ran the Llama there and asked the question, he got the answer. right? So it's like Olama on your laptop is like you have a genie or no in your box kind of thing, right? Is there another question?
This is it for the time being.
Oh, nice, thanks.
You can
Okay.
go ahead with your presentation. Okay, sir.
Yes. I'm terribly sorry that I don't know black box AI. I've been keeping track of all the AI, so maybe it's a different. Okay. Now comes the large language model plus plus. It's like C plus plus kind of thing. Like the plus plus is the addition, right? What folks realize, like at the end of the day, large language models are just equations. They're giant equation which is trying to remember a lot of things. So if you have to get the full use of large language models, you can probably attach some add-ons, some things extra to it. And one of the main thing is this retrieval augmented generation, or as we call it, RAG. It came in 2020. Obviously, GPT-2 and GPT-3 came later, to be honest, or GPT-3 and or 3.5 came later. But RAG was already there, and I think I also used RAG in some of my papers early on. We used to call it dense passage retrieval. But anyways, the idea of RAG here is that if you are asking a question to an LLM, say ChatGPT, the best ChatGPT ever, the best LLM ever, I'm going to ask like, how many days of paternity leave is provided in my company? So in my case, Celebal, in your case, probably like your own companies or colleges, right? The trouble is LLM doesn't know because it has never seen this data. Even if it has seen, maybe it has seen once, it can't remember, right? Or the information is very private that no like LLM creators have that information. And believe me that this is one of the many asks we get from our clients here in Celebal, that they all want a chatbot which can understand their internal information. And to be honest, this is exactly kind of one of the questions we get, because we in Celebal, we have created a lot of HR bots. So one of the things which happens in companies and maybe in universities is that people keep asking HR that, oh, what should I do there? What should I do this? How do I fill my like how do I get my form 16? How do I how much maternity leave I get? How many casual leaves I have left and everything, right? So that is kind of a thing which we can solve. How do we solve it? Is that you have a question before even you send it to LLM, you use a normal search engine on the documents which you have. So the idea is that any search engine or a search thing like Elasticsearch, Lucene Index, or even Google search, right? Any search engine you use, you look at the question, you get the paragraph which is related to it. Maybe the paragraph is huge and it might have or might not have answer. And now to the LLM, there is a picture of a parrot here, but it's the LLM here, right? You give the question and the relevant documents together to the LLM and say that, by the way, this is the question, this is the document, can you tell the answer now? Right? And that was like what we call as retrieval augmented generation. Why? Because it's generating the answer with the help of retriever. Now the retriever can be a document, retriever can retrieve like web pages, anything, right? So that's what Google is doing now. That's what Bing is doing now. They already have search engines. Now Google also, if you ask some question, they also give you generated answers by looking at the web pages. So RAG is like extremely useful. A lot of clients want it. A lot of people want it. You can also create your own RAGs. Now, another thing which I have a couple of patents and papers around is like answering questions from table or SQL. The idea is that if someone asks like how many leaves I have for me, obviously that's not in your manual or document. It's somewhere in your database. Some admin in your college or company has database in that there is all the leaves, everything taken. Now, what happens here is that it's not just about identifying a document and giving it to the LLM. Here, LLM comes twice. One is that question is looked at by LLM and it converts that question into a SQL query. SQL query runs on SQL. It shows the answer. The LLM tries to rephrase it and make it a language and give an answer. And we have, for many of our clients, we have created these systems and it works amazing. We also sometimes create plots for them. Some like one of the client wanted like, I want to see my revenue for this product in the last 6 months. Our system automatically creates the SQL. It goes through the DB. It creates plots and everything. Okay. Any questions still now on RAG? Because RAG is one of the things which like many of you can work on. Many of the junior students can work on. Okay.
No, I don't think that there is any question. We can
Okay.
go ahead.
Okay, great. Yeah. So one of the thing, right, in RAG is that you can use normal search engine, and then now because we have all the embeddings, like Dr. Amit mentioned, right? There are a lot of these embeddings and everything around, and why are we using normal search, right? Lucene Index or Elasticsearch? Why can't we also use this embeddings? And the good thing about embeddings is that if someone is asking my mother passed, or like my grandmom passed away, and then I want some leaves, right? Obviously your manual doesn't have like grandmom passed and 5 leaves, right? So what it comes under bereavement leaves or whatever, right? So probably I'm getting the word wrong, but there is a word for it. Now, like, you want your retrieval also to understand that the mother passed, or the that is connected to this complex word of bereavement leave, right? And obviously the word matching or the character matching is not going to solve it. So what do we need? We need again the embeddings and the word to word kind of thing is coming back. A question comes, we have an embedding model here. Why we are calling it embedding model? Because it just creates embedding. It just doesn't do anything. There's no generation, nothing. It takes a document, it creates a vector. It creates a question, it creates a vector. And then so the vector is in some 300 dimension, 1000 dimension, it doesn't matter. And now, once you have all the documents like this here in this green, or sorry, the blue, and your query is in orange, you try to look at the similarity. So the idea is, why should the similarity work? Why? Because this embedding model is trained to tell that if there are two things which are close by, they should have their vectors close by, right? And there is a huge story on how to train this embedding models, and there's like back and forth, a lot of research and innovations there. So we need not go there, but the idea is that there are the embedding models. ChatGPT also provides it, as in ChatGPT is not an embedding model, but OpenAI has services to create embedding models, right? And then you can also save these vectors in vector DB. You'll be like, why do I need DB? Just numbers, right? It's not like I can query different ways. You are right. Vector DB can't be queried in different ways. You can only query in one way, which is like, given this vector, which is the closest other vectors. And in this case, given this query vector, which is other close relevant document vectors, the reason we have vector DB is that if you have huge amount of data, you have like 10 million documents. So do you have 10 million vectors? Now you have a query vector coming. And if you want to find the nearest one, what would you do? Like, you keep matching. If it is order of n, you have like 10 million similarity measurement you have to do, and then you get the best. But if you do vector DB and like, I don't know if you remember KD tree and all those kind of data structures where you can save this input so that the parsing becomes log n, right? So that kind of trick you can use, and vector DBs helps do it. A lot of vector DBs available. You can just put the vectors and they just get all those indexes correct. Indexes like this KD tree and stuff. Right, it can only do one thing, just like similarity measurement. That's it. How it is trained? That's a good question. So the trouble with training, right, is that again, where is the training data? Do we know these sentences are similar or not? The idea is, again, you take unsupervised data. If there is a sentence which is coming nearby in the same paragraph, they probably are similar. If there is a sentence coming here and the other sentence coming from another document, there's a good chance they are not similar. So you just have these similar and dissimilar pairs, and you make sure that similar pairs coming close by. So dissimilar coming stay away. Have some equation, objective function. Just train the model and get the embeddings. So that's what text embedding does. Now, towards the last 2-3 slides is that there is LLM agents. That's like, see, retriever is not just solving all my problems. There are other issues which I have. For example, how many US citizens have more than 20 million citizens? Like, how many US cities have more than 20 million citizens? LLM can't answer it because it doesn't have that kind of information. It is somewhere in DB, which I don't have access. But if I have Google, I can use it. So I will do like agentic LLM, what's called. I can attach a search engine to my LLM. How many teeth does a person have? That it can remember, but how many teeth does a math teacher have? 47. It's giving wrong answer. These are a bit older LLM, but it's still giving wrong answer because it's not able to connect teacher as a person. So you probably have some thinking needed. What is the date today? Obviously, all LLMs gets this wrong because there is no time. Doesn't have a clock to look at. Number also was a big issue. So essentially what happened, you can look at the left side, is that the idea was that language models need to have a lot of tools at its hand, so that if there is a question coming and it understands that I don't have that information with me to answer, for example, what is the date today? It's Sunday or it's Wednesday today. Like, that information is not needed. So then LLM can take a call that, okay, I need to call my calendar and get that date. Right? So calendar becomes a function. It's like a tool. then you create all these tools, like tools for calendar, tools for currency exchange, weather API, databases, tools to work with math, tools to do a lot of things, right? All of these things you keep, and you also give this information to LLM that these tools can do all these tasks, and LLM takes its own decision when to call each of the tools. And that is what we call LLM agent or agentic LLM. And this is the high level architecture of how it works. A user request comes, there is an agent, which is agent is essentially an LLM inside it and some wrappers. And it will take a call. Should I ask a tool? Should I do some planning? Because some questions need planning. For example, if I say that, write me a code which will create a game similar to, say, like ping pong. Sorry, Pong, which is this 1980s game, right? Pong game, right? And then obviously, like, it can't just go on writing, so it will do some planning, and like, so LLMs looking at its own generation and all those things came. So this is the high level thing. I'm not going to talk a lot about it, but this is the next biggest thing. If you are looking at what things to build around the LLMs, I would say LLM agents is the place where you can do magic, right? Yeah, sorry, I took a lot of time. I think I have maybe 5 more minutes one more slide, but that's like the last slide. Anyone has any questions on this plugins part? I didn't cover a lot of them, but if you have any questions, I can explain. We have created a lot of these models for our clients, and we can explain some of them.
Okay. I think there is no questions from the participant side till now. So
Yeah.
I think we can finish it up, then we can take few questions from the participants.
Oh, no, okay. I just only one thing. Like when we started with contact center, one of the thing was that when the conversation is happening and we want to understand what they are talking about, and is there a suggestion the LLM or the AI system can give. There, what we were doing is that we look at all the conversation. We kind of do a LLM to summarize the conversation. Then we look at the summary and see that is there a problem they are facing, and is there a solution we need. So there is a problem, we extract the problem. Then we use the RAG model, which we see here, right? And sorry, here. And the RAG model, this problem goes in, it goes through the whole manual of the bank data and then comes back with, say, like 10 or 5 candidates. And then we look at all this information and say, is there a suggestion which I can give to the user or not? You don't have to give suggestion always. So that's a bit like this agentic LLM which we have created, and it was working fine. Right. So just the LLM is not going to solve a lot of things. You need to create this agentic LLM. A lot of this effort is about giving correct instruction to the LLM to do these tasks. You have to essentially, all of us become this kind of English lecturers trying to teach students what to do, and you kind of use different words and examples so that the student is doing great. So in other words, this is what is called prompt engineering and prompt tuning, right? Instructions we have to give correctly. This is the last task, last slide. Things I didn't talk about is that the reason LLMs became this humongous thing, like maybe at the time when I was starting, which was like 2011, 2010, like this AI was a small thing. It was probably like a small turtle, which has kind of become this giant dinosaur now, is because of GPUs. Because CPUs, we were not able to train model. Training used to take weeks and maybe 2 weeks. But because of GPUs, the training became easy, so people could take more data and everything, right? So GPUs and NVIDIA created GPUs were just the reason. Kind of, we can give a big, big contribution to the GPUs which NVIDIA created, and thanks to also video gamers, because that's the reason NVIDIA was always creating better and better GPUs. So then NVIDIA found that AI and LLMs, they were all asking for bigger and bigger GPUs. So NVIDIA started creating GPUs specifically for the AI people, hence the A100, V100, and H100s, right? Then the other one is this open source libraries, such as I also mentioned, PyTorch, TensorFlow, Hugging Face. They all had a big game in creating these LLMs and the whole bringing all the community together. Till then, to be honest, everyone was writing their own code and their own small libraries. Every research lab, every company used to have small library they used to work on. But PyTorch, TensorFlow, and Hugging Face, when they became open source, everyone could just do and train their own model, just like some 10 lines of code, 20 lines of code, and became a biggest thing. Then there are other things which you guys already know. Folks already know, is like LLM sometimes hallucinate. Nowadays, hallucination has gone down, but earlier the hallucination used to be a lot, which means that it used to tell things which is not true. So obviously, don't believe everything LLM says. Always verify if the answer is very crucial to what you're doing. There are vision LLMs. Dr. Amit has talked about it. I have not talked about vision part at all. They can look at images and also text together and do some answering and question answering. The VQA question someone was saying, visual question answering, it can do. Models and this word to work when it came was that word to work used to always say that doctor is to man as nurse is to woman, right? And that is those are the subtle or not so subtle gender biases which used to come from the human way or the our line, because these AI models are essentially trained on the text which is available in the world, and those text and the humans in the world are biased, so that's also creeping into the AI, and there is a lot of effort people are doing to make sure that those bias doesn't stay there, and we also do that. Yep. So yeah, that's pretty much it from our side. Any question I can take? I'll be happy to talk. Talk about.
Uh, uh, yes, sir. So there is one or two question, I guess, from the participants. So what are the requirements? Maybe like in the form of GPU requirements for fine tuning LLM, like Mistral and Llama.
Oh, fine tuning is it?
Yes.
GPU. Okay. I will have to check. So obviously there are like different llamas and different types of sizes. Uh, one thing I think Mistral which model? Okay, if you pick the smallest llamas, I think you can go with the small like A100s or even model uh, in a smaller data and in a smaller compute, right? Earlier, as I mentioned, you don't train every like 1 billion or 100 billion variables in the model. You just attach these small equations called adapters and just train them. There's a lot of math and amazing equations available. There's another, okay, now I can see because I'm not sharing. So max topic
Yes.
general element and many more. If possible, share PPT to us. Yes, I'll share the PPTs. One of the bad thing about my PPTs is that they have more diagrams and less text. So I'll
Yes, that is more descriptive. So that is
yes,
very much fine.
yes, yeah.
Okay, so any questions from the participant side? So
Yes, yeah. Any
so
questions you can ask?
please you can unmute yourself and you may ask questions.
Yes, yeah. One other thing, and like I probably again tell the same thing which Dr. Amit told, is that Sellable Technologies is a company here in Jaipur. We have like headquarters here. We have like a couple of 3-4 offices. We have 2,000 odd employees. We also take interns, and if you have like very bright students who wants to work on cutting edge AI and LLMs and work on, you can send their CVs on our
Definitely.
way, and we'll also work on it. um, yeah, I come like from a very different background. I have worked really very mathy side of it and applied side of it. So yeah, so we can work on it.
Definitely. Okay, sir. So this session is was very insightful and engaging actually. So it
Okay.
began with an NLP and it's covered like a wide range of application. You have also
Yes.
talked about the encoder models with attention mechanism leading to the transformer also, which you
Yes.
describe as just steroids in this particular field, and it is quite interesting description about it. And you also
Yes.
talked about BERT, GPT, and highlighting their capabilities to impact on the what is their impact on the NLP task. So it is
Yes.
a very nice way of explaining these things. And you already also talked about the real world application. Thank you, Mr.
Yes.
Sani Mohammed, for
Yeah,
providing
thanks
such
a
a
lot.
comprehensive perspective on the
Yeah,
evolution
thanks.
of
Thanks.
this LLM.
Yes. Yes.
And
I
there
think
is another question from Dr. Arpan. Can we connect with you for student internship? He's asking.
yes. Yes. Yeah. You can connect with
Yes,
me.
obviously.
I
Yes.
can. I can. What I would suggest
So,
is that we will obviously have a like a filtering,
uh,
obviously,
sir,
right? So
Mr.
I'm
Sanim,
just putting my
you can
email
share.
ahead,
Yes. Yeah, yes. That is.
right?
Yes.
One of the thing, right, is that again, I'll come very practical, right? Is that
Yes.
we are
Yes.
creating a lot of clients and products and everything. One of the thing which we don't get enough time, like earlier I used to get in IBM
Mhm.
research and Microsoft, but I used to get enough time to do research. I used to get enough time to come up with some fancy stuffs.
Yes.
Currently, I'm
Yes.
kind of stretched because we need to create products, we need to sell it. So research is a bit of thing which I don't get enough time. So if there are like nice bright students who are really keen on research, who can help us do some nice experiments, and yeah, maybe. So for example, right, one of the thing which I work nowadays is that LLM for time series forecasting,
Yes.
right? It's a very niche topic. There are like very few people work on it in the whole world, right? It's about like, can you use LLMs or some versions of LLMs to do time series forecasting? How does it help? How does it not? So there are a lot of things we are doing. There is also some of the research kind of work. We are also trying for some patents here in Cerebral as well. Is that like when most of our clients have a lot of data and they want to do some EDA, exploratory data analysis, you look at plot and you say that, oh, I
Yes.
have this issue with my data. Can we use LLMs to help do this data analysis automatically? Right?
Okay.
So rather than like person writing code and telling, show me the histogram, show me that, show me this, can LLM take like person say that, okay, what like tell me about the data, and then it shows a lot of plots and stuff. So that
Right.
is like
Right.
kind of
That.
some. So what my point is that if you're sending interns, like towards me,
Yes.
like these are the kind of the things they'll be working on. So yeah.
Yes. That is
About that.
that is the more interesting research domain you are talking about.
Yes,
Thank you.
yes, yeah. So like there is a
Okay.
thing, right? Like if you're a researcher, you're always a researcher. So it's I've kind of moved away from research, but there's always this
Yes. Yes.
like in putting Hindi, right? There's always a research kida in your head. You always want to look for those novelty and
Yes, definitely.
innovations.
Definitely, sir. Definitely. Okay, so I think that all the queries being answered by the resource person. And Preeti madam, can we wind up this session?
Yes, this has been a very thorough, very interesting session, and we are grateful to Mr. Saneem for joining us despite a very hectic schedule at Syllable.
Yeah,
Uh,
thank you.
yes, and regarding the interns, we would also definitely like to collaborate with you. I think already LNMIIT has an MOU with Syllable, but we
Oh,
are
nice,
like,
yes.
yes, so I'm having a very bad network today. I don't know why this problem. So I'm just keeping my video off. So, but we hope that we will have a like a physical interaction with you also in the near
Yes,
future.
yes, sure. Yeah, we're in the same
And
city. It helps.
yeah,
Yes.
yes. Thank you very much for joining.
Yeah, yeah. Thanks everyone. Thanks for being very kind with your feedback. Thanks a lot. Thanks, Preeti, again for inviting for this talk.
Yeah, thank you so much.
Thank you
Thanks,
so
everyone.
much. Okay.
Will you end the call, Nikunj? Okay.
Yes. Good night, all.